leaves Rio de Janeiro, carrying 216 passengers and 12 crew to Paris. Weather reports indicate severe thunderstorms along the flight path.
Fuck that nigga.
3 hours and 45 minutes into the flight, as the plane nears the equator, its onboard computers send a burst of emergency warnings. Then falls silent. Olivier Ferrand is in charge of the French search team. The warning signals are his first clue.
Some maintenance messages and an important position message, which was very useful for search.
It's a deep and remote stretch of ocean, but the search team has every advantage. Unknown flight path, an accurate final position, and then surface debris found within 5 days. And yet, despite initial optimism, it takes 2 years, 4 expeditions, and $40 million to find it.
Yes, and to that moment, when we found the wreckage, I was very careful, because we've had the false alerts before, that it turned out to be geology or not what we're looking for.
Why does it take so long? Using the data meticulously collected by the search team, combined with the latest visualization technology, it's possible to drain the Atlantic Ocean, revealing the hostile world that faces every deepwater searcher. Immense water pressure, freezing cold, total darkness, and hidden dangers everywhere. Finally, at 12,800 feet, the shattered remains of Air France 447. Engines, wheel assemblies, and other heavy items lie together. Their twisted remains a testament to the force of the impact. Smaller, lighter objects stretch along more than 1/3 of a mile of seafloor, equivalent to 8 New York City blocks. And a critical realization: the seabed wreckage is nowhere near the surface wreckage. It's almost 24 miles away. Investigators spend about 2 years searching in this very challenging area, not realizing that ocean currents have carried debris far from the crash site. The long, frustrating search for the French aircraft carries a warning. Even with debris and an accurate final position, when a plane goes into deep water, it's very hard to find. A sobering thought for the team searching for MH370.
Air France was very difficult with our area of 17,000 square kilometers, but it's nothing compared to the surface that the search teams have to search for MH370. It's much more difficult.
In the southern Indian Ocean, investigators look for surface debris for over 2 weeks. Even with the aid of satellites, they find nothing.
One of the greatest initial mysteries, and that has transcended the entire period of time that we've been looking for this airplane. Where's the debris?
With no debris, they need to find another way to narrow the search. So they focus on MH370's black box data recorders. Each has an underwater locator beacon, or ULB. In water, they emit an electronic ping with a range of just over a mile. Find the beacons, and you find the plane. But time is running out.
Battery life on the ULBs is only 30 days. Although they do last longer, they fade out.
By the time the specialized pinger locator technology reaches the search zone, there are just 3 days of battery life left.
Let's see, 311.
Yeah, 311.
Investigators have only a few days to locate MH370's black boxes before their locator batteries run out. Faced with a vast search zone, they decide to focus on commonly used air routes. To the locator. You're not lost. Here is a search ship passed directly over here, but detected nothing. The metal wreckage may have blocked the signals, or they could have been damaged by the sheer force of the impact.
I think they were unfortunately damaged at that stage.
Investigators listening for the MH370 black boxes can only hope they'll have better luck. They monitor the ocean for 15 days, using 3 ships equipped with sensitive listening technology, while military aircraft launch sonar buoys. They do detect some signals, but conclude it's just random interference. It's another disappointment. But at this low point, there's a dramatic new lead. A team from Curtin University in Western Australia runs a network of sensitive underwater microphones called hydrophones. Positioned all around the Australian coast. They're designed to monitor earthquakes, Antarctic ice, and wildlife. And remarkably, one of them has picked up an unusual noise. 1 hour and 14 minutes after MH370's last communication with the Inmarsat satellite.
When we looked at the data from that hydrophone, we found one signal that looked as though it had interesting characteristics.
Is this the actual sound of MH370's final moments? Alec Duncan's team looks for other audio recordings so they can calculate a geographical fix.
One hydrophone does tell you a certain amount about the source of the signal, so you can tell whether it's a whale, you can tell whether it's a snapping shrimp, you can tell whether it's just noise from the mooring, but you can't tell direction.
Fortunately, other agencies are listening too. For the sound of illegal nuclear tests. Technology that can accurately pinpoint the source. Just off the coast of Cape Lewin in Western Australia, the Comprehensive Nuclear Test Ban Treaty Organization runs a listening post, specifically designed to detect and locate illegal nuclear tests. The station has 3 hydrophones set 1¼ miles apart. They can determine the direction of a sound to within ½ a degree and calculate the distance to the source over thousands of miles. And astonishingly, this network has detected the exact noise heard by the team from Curtin University.
The analysis of the data from Cape Lewin told us that that signal had come from the northwest and gave us a fairly accurate bearing along which the source of that signal must have been.
It's a tantalizing clue, and the sound does come from the direction of the 7th arc, But when the scientists crunch the numbers, the source of the sound is far to the northwest, so far beyond the current search area that it's considered not worth further investigation.
Our conclusion
Probably
was
the
that
origin.
the signal was most likely to be of geological origin, such as a small undersea earthquake, but we can't completely rule out the possibility that it came from something to do with the aircraft.
Faced with a new disappointment, the search team moves to a different approach, searching the seafloor itself using towed sleds carrying sonar scanners. It will be the largest undersea hunt in history. But before it can even start, there's a new problem. This part of the Indian Ocean has never been surveyed in detail. The sleds will be close to the seafloor, and no one knows exactly what is down there.
We knew we'd be operating vehicles very close to the seafloor, which necessitated knowledge of what was down there, and so that we could avoid collisions with terrain.
The MH370 team needs a simple way to create a snapshot of the seafloor across the vast search area. They find help in an unexpected place. The team hunting MH370 across 463,000 square miles of Indian Ocean faces one big problem.
More than 99% of the seafloor area in this region has not been covered by ships with modern equipment, satellite navigation, multibeam echo sounding.
Geophysicist Walter Smith thinks he might be able to fill in the blanks using satellites.
The satellites actually cannot see the bottom. They're not seeing the ocean floor. What they're doing is using radar to measure variations in the sea surface height. Water is
It's possible thanks to gravity. Mountains on the sea floor create their own gravitational attraction. Surrounding water is drawn towards the mass, creating measurable changes on the surface.
The smallest ones I can resolve are a kilometer or less in height, and they move the sea surface